So let us discuss the lambda, the weighting. So here we assume our weighting, the R equal to that, and also we assume Q equal to 1001, and that's the result we have for this case. So when we give a very large lambda, and the lambda has to be larger than 0, so the lambda can be any value larger than 0. When lambda is very large, that means my input will be very small. Larger lambda means small feedback here. So we are here, right? Large lambda means small feedback. What does that mean? So we know that this R is the one to weight the input. Right? R is the one to weight the input. If we remember Rj, what is Rj? J is 1/2 what? That's x q x, no, y cube. That's L Q L plus U transpose R U, right? Like that. Well, you need to go back to a few slides back. Our cost index. So if R, the R is this 1001 lambda. So if R in terms of lambda is very large, that means my U, my result U, will be very small. If R is small, close to 0, then your U will be like this. As a matter of fact, that U will be like this. Approach to that. Assume this E11 at 1001. Okay? So we can conclude that if R is very large, it has to be this way, then my feedback U will be very small, supposedly, right? Okay, here I also give you a proof that if you insert k equal to 2, 3, and to n, then you will find out that based on these formulations, U2 will be minus 1 over lambda plus 1 parentheses UC1 plus U minus 1 lambda plus 1 and U1 and U3 and so on. And there's some important concept at the end there. I want to show you what is it. All right, this is so this is very practical methods. You can use for a lot of different systems. I want to show you all the concept here. And if you have UCC means control. UC UC n equal to here minus 1 lambda plus 1 then n minus 1, okay, then that's UC1 plus, then that we have that lambda plus 1, I just copy this one so I can explain better, n minus 1 y1 plus and so on plus that the minus 1 lambda plus 1 and y n minus 1. Okay. Now there's some concept here we need to look at that. We know that lambda must be larger than 0. Right? That's because we have to have the positive definite. Positive definite R. That's equal to lambda 1001. So that means larger than 0. What does that mean is if lambda 1 that if minus 1 not plus lambda 1 n minus 1 will be approach 0 for n approach to infinity. Agree? All right? Right? If lambda larger than 0 means this term will be less than 1. If less than 1, if n is very large, then that term will approach to 0. Agree? The same thing here. All the same thing here for what? For this second term. But this one here, this, if n, okay, also that imply that y for n approach to infinitive, then y n minus 1 will be approach to 0. Know why? Anybody tell me why? I say if n approach to infinity, then y n minus 1 approach to 0. Why? This is because our design, we already set, because we set our desired output right? We already, before we derive this, if we go back to our slides, we set here, 0 desired output. So our formulations that our control force supposed control a system such that when n going to infinitive, that's supposed to be approach to my desired output. That means that, let's see. What does that mean? So when lambda larger than 0 and n approach to infinitive, then UCN will be equal to, will be approach. Agree? Are you agree or not? That's an important concept. I will explain to you. All right. Now, my control input. In my control input, when my output approaches to zero, my control input does not approach to zero, what happens? We need to say this. If the output y and approach zero, but my control force n not approach to zero. What does that mean? What does that mean? The ideal case is when my output approaches zero, my input also approaches zero, right? Because my output is already zero. Why do you need any control? You don't need any control. Okay? So when you design a controller, you gotta make sure that when your output approaches zero, your input also has to be approached to zero. If not, means my output is already quite there, but your input is still working. That's not a good control. Although it may be okay, but you better turn off. When you've got this case, when the output goes zero, but my input is still working on it, you better turn off your controller at that moment. Because your controller will excite your output again. So, in this example, I just try to prove to you that my controller design, although my D equals zero, that's a nonlinear phase, my controller is still good because when my output approaches to zero, my input also approaches to zero. When time, if you give them enough time. Understand? So this final step, just try to prove that our controller is, we call robust controller. This is what we call robust controller. So, if the output approaches zero and then if my output y to zero and my input n is also approaching zero, that means we call robust controller. Let me I need to say a few words. Most of the controller, they are not satisfied with these conditions. I say most controller, they are not satisfied with these conditions. All right. Now, also, for this case, if lambda equals zero, lambda cannot be zero, but assume say lambda approaches to zero. Then, if lambda approaches to zero, that U, if this is become like a 0, that UC will always get value here. Doesn't matter how much Y you got. Think about that. If lambda equal to 0, then UCN equal to minus this UC1. They always got value. So if you put lambda 0, you put lambda equal to 0 for your weighting, then your controller won't be, I call, robust controller. Understand now? So, doesn't matter what controller design you try to produce. The best controller will be when output approaches to 0, then your controller also, your control force also approaches to 0. That's the ideal case we want to have. So this is, for this case, UCN approaching 0 for lambda larger than 0 and N are going to infinity. And that we call stable controller. Also is a robust controller too. This is we call stable controller. There are many cases, controller itself is not stable, but your closed loop feedback, your clock system is stable. We make a little remarks here that if you let me say it was here. Now, closed loop system stable does not imply the controller itself stable. In many cases, matter of fact, in most cases, closed loop stable is stable, but controller is not stable. It's not stable. Okay? All right. So that's when you design controller, you gotta watch out this kind of things. It doesn't mean that these cases, the controller is not usable. I didn't say that. Right? Even that. But the controller is not stable. But even that, the controller is still usable. You can still use it. Okay. Any questions? So for this simple example, there are a lot of concepts involved in here. Now I want to tell you. And it also, in predictive control, this is the case that stable controller doesn't mean all the predictive controllers are stable. Not like this, no. So when you use a predictive controller, you still be careful too. There's still some cases, lambda, given some lambda value, that the closed loop system stable, but the controller is not stable. Okay. Now we finish the predictive control examples. Now I'm going to discuss some of the features of the predictive control. Okay, we have to be, let me just list all this down, then we can talk a little bit. Now, predictive controller, now we use a strategy. Current control action are based on prediction of the system response. That's the output prediction matrix, the equations we have. There's a system identification involved in here. So the predictive control is still here. There's a concept here because there's a system ID involved. Right? We have system ID. We have to identify alpha and beta. Now, so the system ID is involved in this predictive control design. That means predictive control is model dependent. We know ABA is not model dependent, right? We learned that. But predictive control, we do need model, like ABC, that example I give to you. We have ABCD. Based on that ABCD, that model, you can design a controller. The system ID really provides you the model, although they really provide you alpha and beta, mean observer macro parameters. Now, observer macro parameters are the observer models. So we should say that predictive control is model dependent controller. So you say predictive control. Just right here. Predicted with control method. Is model dependent. That means because your output and input are model dependent. Your output is model dependent, right? Okay. And this we have called OMP here, called observer macro parameters involved here. And that macro parameters, observer macro parameters called OMP, also model dependent, right? This OMP also is also model dependent. The model dependent made ABCD. We have A, B, C, D. So ABCD allows us to compute A, O, and B. ABCD will give us the output. Although in the predicted control process, we really don't need ABCD. We need just to observe macro parameter alpha and beta. Okay. Now, there's a formula here called P value, the P value. Let me explain to you a little bit here. Assume this is a system. We will have this one too later. And this is my control input. That's my output. Called Y. This is my input called U. And there's some disturbances. There's some disturbance. We usually call DE2, disturbance. So, for example, this airplane, and there's an engine, there's aerodynamics, that's my disturbances that we are open. That disturbances here, if you look at these disturbances, I have P, the P that's larger or seal. You know, this seal, you know that, right? This is the side or magnet is that. And this is a number M. This is number of outputs. Alright? And then there's N system order plus the N disturbance order. Alright. For example, if my M equal to 3, okay, my number, the order, system order, number system order, that equal to say 10. Alright. My number of disturbance order we call say 5. Then P will be larger than equal to CL, then that's 10 plus 5 divided by 3, that's equal to 15 divided by 3 is equal to 5. That P, remember that P? That P means that determines the size of the script T matrix. Right? Although the size is related to HP and HC, you know that HP and HC in the output partition matrix. So this is the order. This is okay. Let me just explain more about this P. That P means YK. For example, YK equal to alpha 1, YK minus 1 plus alpha 2, YK minus 2 plus alpha P. k minus p, right? Plus equal to beta 0 uk plus beta 1 uk minus 1 plus beta p uk minus p. Right, that's the p. You know that p? That's the p. In other words, the current output can be computed from k minus 1 up to k minus p. That's the p. In other words, if you know the order of the system, you know the order of disturbances, you know your output number, then your minimum p has to be chosen to be this number. That's the minimum. For example we have, let us get our example. Erase this. Right? Example we have. M equal to 1, right? Single input, the single output. And then we are our N system order equal to 2, right? Alright, and then the system order. And then our N disturbance equal to 0, right? We don't have any disturbances. So our P must be larger or equal to that 2 plus 0 over 1. That means 2. Right? That's our example. So that result T, that result is script T. So that make that our script P is a 2 by 2. Our A, script A is 2 by 2. Our script B is 2 by 2, right? 3 is that P. So that is, this value is important for practical applications. Now you might say, how do I know the order of the system? I don't. I don't know the order of this building. So what kind of PS you're supposed to keep to put? I'm saying it has to be large or equal. So if you don't know your system, say I don't know my system. I don't know my order is how much. Then you can pick up a large value, start with a large value, because that's large or equal. You can start with a larger value and design your controller and try it. Understand? In general, yes, I don't know the system. This is why we need system ID. We have some data of the system. Then from the spectrum, we might be able to see how many frequencies we have. Assume the system has 5 frequencies. Then what's the N? It has its frequency represent 2. So 5 frequencies will mean 10. N is equal to 10. So generally, in real applications, we choose a P, a large P, to begin with. And then we can design controller and try it out. If it performs, you're satisfied it performs, then it's okay. If not, then you will be able to change to P and then try it again. Alright? Now, this is the HP and NC. the control horizon and petition horizon, SP and SC. Normally, in most applications, we set SP equal to P, SC equal to P. So in real applications, in most cases, we set HP equal to HC equal to P. That's almost in all applications so far we set, because we like to minimize the parameters we have to do. As long as you set this, then you should be okay, because there's an equal sign there. All right. There's a lot of things going on for this method, and I just explained part of it. Here are matrices Q and R are control effort and tracking error. The tracking error for Q and control is for R. Matrix T is invariant if system does not change, because it is formed from system macroparameter. I explained to you already that tau, this tau is formed by pulse response, right? And in system ID, the pulse response we call system macroparameters. So T is formed and is invariant, means it won't be changed if your system doesn't change. So that's T. However, that's B are not. The squid A and squid B are not really unique. Well, T is unique for a given system. Doesn't matter how much P we're talking about. See, this is formed by pulse response. So your P value, you change the P value here is, so the T is not, that means it's formed by, so that means does not depend on P. Are unique because they are P dependent. Right? So tau is formed by pulse response. So when you change P here, doesn't matter, because it's just the pulse response are not changing when you increase your P value. No. The pulse response is unique for any given system. It has nothing to do with this P value. But this group A and B are not not just only system dependent, they're also P dependent. Okay, be careful of those. This is, I already proved to you this, right? But I didn't really prove to you that. But anyway, I'll just give you this kind of these properties, these also characteristics of the predictive control. All right. I'm not going to talk about too much about system identifications because that's not cross. All right. Then the computation-wise, there's a system identifications you need to be aware of. Pseudo-inverse based on SVD, online real-time reverse process online. I think this is too much since I have to explain here. I'm not going to explain too much here. Okay, now here you go. That's also very practical consideration here. A lot of things going on here. I don't have enough time to do it. Plus, some of these features you need to have a background of system ID. If you don't, then I don't know how to explain to you. So if you taught my class last semester, then you will understand what the micro frequencies here is, and so on. And here, because if you don't know anything about system ID, it will take 1 semester for me to explain to you for this. We have only less than an hour left. Okay, jump. I jump on this and give you some hint, some example, and for you to understand what's going on here. Okay, I'm going to give you some simulations using NumMath, as you know that a lot. And I'm going to show you some experimental results using the predictive control. And there are many, many examples, and I can't just talk all of it. But this is the example we have done in 90s, and also the beginning of the year 2000. Let us look at the simple example here. This is a very simple example. These are 3 different rhythms that here. There are 3 different rhythms. And this is just only a very ideal case. We assume that we have a negative decimal, negative value for decimal. That means we have an unstable system, which is impossible in real case. But we just try to show you that the predictive control is also applicable for unstable systems. That's the purpose. And the system is unstable. If you don't control it, it's going to grow. The responses are growing, so it's an unstable system. Now, from 0 to 5 seconds, because here we have the U1 here is the control input. U3 is the disturbances. So I'm talking about there's a disturbances involved in this example. U1 here, where U1 as the control input. That's for my predictive control. Let me explain to you a little bit here so you know. Now, when you try to apply this method for your real system, you can do the same way. E1 here, E1 is my control. That's my control input. My control input. And the U3 That's the disturbances. That's we just give them one frequencies. That's one sine wave. So in the open loop, because we have usually disturbances of one frequency, assume these disturbances are known. All right, we don't know anything about these disturbances, but we know that there's a frequency involved in it. Only one frequency, but we don't know what kind of frequency we got. We just know that there's one frequency disturbances unknown excite the system, just like earthquake. Sunday we have earthquake, right? So the earthquake coming with one frequency. I don't know what kind of frequencies of that earthquake. But in Taiwan, we know that it has to be less than 15 hertz. That's our frequencies. Just we know like that. So if we have no control, then you will see that this is open loop responses, because disturbances is keep growing. Because also this is unstable. This is unstable the decimal. Now, the control input, we also give them a little bit control input. The small call excitation input. Random input. All right. This random input, we know that we give the input to a system too. So the system we have giving control input that is small, that's random. We have disturbance input, that's unknown, that's one frequency. So from 0 to 5 seconds, we have output. This is our disturbances. That's assume that's only one of the frequencies. All right, and then this control input. This is our external disturbance usually, and this is our open loop responses. Assume we have no control feedback for that. Now from 0 to 5 seconds, we know control input. So from 0 to 5 seconds. Then we have control signal and output response. Okay? So from 0 to 5 seconds, we have control signal, that's E1. And this is Y1. Y1. Okay, that's my Y1. That's W1. Okay. As a matter of fact, this is acceleration. So Y1, we have the equal to W1 double dot. That's the accelerations. So from 0 to 5 seconds, we have a control input E1, and we have our output response Y1, that's the acceleration output. So that we have, so 5 seconds input and output history. So we have 5 second input and output history. From this 5 second input output history, we will be able to design to do, then we do, and we do system ID and compute control feedback. We call UC. K, right? That equal to alpha 1 C y k minus 1 plus alpha 2 C y k minus 2 plus alpha C P y k minus P, then plus this C beta 1 C U k minus 1, this is C, plus beta 2 C U C k minus 2, plus beta P C U k minus P C. Okay? So from this 5 second, we do system ID, then we pick a control feedback, we compute UCK equal to this is, so we are, from this 5 second input, we'll be able to compute R1C, alpha 2C, and so on. This system ID will allow us to compute alpha and beta, not C, just alpha and beta, the observer microparameters. So from that, then we'll be able to compute this. Now, after 5 seconds, because we have enough data, 5 second data, for us to do system ID. That system ID will allow us to compute alpha and beta. And then from alpha beta, we'll compute alpha 1C and beta 1C, right? This is what we got. Then, so after 5 seconds, we turn on, controller, turn on. So that's 5 seconds here. Then we turn on the controller. After the computer, we turn on controller. Then you can see that the closed loop responses close to 0. You understand the process now? Okay? Understand? So we have to take about 5 seconds. For this case, we take 5 second data, the input-output data. From that, but we don't know we don't know the U3. Here, we have no information about U3. We have only U1 and Y1. Y1 is the acceleration data. And from this, then we compute system ID, we compute alpha beta. From alpha beta, we compute this. Alpha 1C, alpha 2C, alpha PC, and beta 1C, beta 2C, and beta PC. As soon as we compute those, we turn on controller. And you got it. Then you have that. We'll take 10 minutes break.
Okay,